Okay, so this problem deals with a banked roadway. Feel free to pause right away to read the problem statement. I'll let you read it. I just don't want to make these videos super long. Okay, so after reading the problem statement, you can see that we have this car and it's basically traveling around in a circle. So we have this roadway. The car is moving with uniform circular motion, okay? And if we imagine there's like a radius to the center of the track, we're given the value for that radius, right? 35 meters. So we want to design a banked roadway, okay, which means that it's up at an angle so that the car can drive around at this speed and not slip out. Normally, when we have a car traveling on a flat plane, we are looking at some static frictional force to prevent it from slipping out. So the static frictional force would be acting against the centripetal acceleration, basically, to keep the car from slipping. So in this case, we don't have that. And so instead, what we're doing is we have this banked piece. So, okay, it's accelerating around in a circle, which means that centripetal acceleration will always point along the radial direction to the center of the circle, so like along the radius to the center. So if we're looking at this so this is like a top view. This is the side view. So from the side view, it's going to be the same, right? We have the centripetal acceleration. This would be pointing towards the center of the circle. Notice it's going to kind of be at like a right angle to your weight over here. Okay, so that's just kind of a high-level overview of what we're doing. So car traveling around in a circle, constant speed. So we know that we have centripetal acceleration. And then we're going to look at a couple of things here. So we're going to start, number one, with what we always do, our free body diagram. So this problem actually already gives us a free body diagram. But just to kind of recap for the pieces that would actually be important. So we would have a normal force, right, that would be coming up because the normal force is going to be at a right angle to the surface, okay? So the normal force, and then the weight would just be acting straight down, okay? So also, if you kind of have trouble getting this angle, remember, we always talk about the angle between the weight and the normal force is the same as the slope if we're up on a slope. And you could use that piece, right, to figure out that, okay, oh, this is the same line, this is the same line, so this theta be equal to this theta here. If you have a different approach, you think that is a little more intuitive for you, feel free to follow that as well. But that's just sort of one example of how you might be able to interpret what that angle is. Okay, so do dot, dot, dot going up. This would be theta. Okay, so free body diagram, check. All right, next we're going to look at sum of forces. Okay, so for sum of forces, when we're asked to solve for something in a certain condition, we have to ask ourselves, like, okay, we want it to behave this way. Let's do our sum of forces, and then for our behavior, we want to ask ourselves, like, what it's equal to. So we have to figure out acceleration in our directions here. Okay, so when choosing our coordinate system, we always want to choose, if we have an acceleration along a direction, we always want to line up one direction of our coordinate system with that. So what I'm going to do is I'm going to choose positive y and positive x. So a little different than what we're used to doing with a slope, but it'll work out okay. Just kind of trust me here. Okay, so let's do sum of forces in the x direction and sum of forces in the y direction. Okay, so for sum of forces in the x direction, note that we have, we're going to break up this normal force because it's the only thing that doesn't lie along the coordinate system that we picked, right? I picked a coordinate system that went along y, right, and then along x. So notice this normal force vector is a little bit off, and so we need to break it up into x and y pieces. That's what they did for us in this problem. They broke it up into x and then into y, okay? So we're going to use those pieces. Okay, so sum of forces in the x, we have nx pointing in a positive direction, okay? So we have nx, and that's the only force in the x direction. Okay, so we look at the rest of our figure, that's it. That's the only x piece, okay? Then for sum of forces in the y, we have ny that's pointing up in the positive direction, and then the force of gravity acting down. So ny minus the force of gravity, which is really just the weight here, force of gravity, and that's going to be equal to what? So let's ask ourselves here. Okay, for sum of forces in the x, do we have acceleration in the x direction that we picked? Yes, we do. We have centripetal acceleration. Okay, what direction is it pointing in? Well, we chose this to be positive, so it's going to be positive. So we have MAC. Okay, and it's positive acceleration. All right, what about sum of forces in the y? What's going on here? Okay, so if we look at the object kind of center of mass here, is anything going to be moving up or down? No. We're moving with uniform circular motion, okay? We're going to stay at the same height on the track as we rotate around the circle, okay? So we're just going to kind of stay in this same plane, essentially. So we're not going to accelerate up or down in the y direction. So, right, we're going to set this equal to MAY. We're going to say AY is equal to 0, and so we're going to set this equal to 0. Okay, cool. All right, now we did our sum of forces. Let's plug in, what n of x would really be. So note that n sub x and sub y. So n sub x will be equal to n sine of theta, right? Because it's across from the angle, sine of theta. And then n sub y would be equal to n cosine of theta, because that sine is adjacent to the angle. So let's plug those in as well. Also, we know that centripetal acceleration is equal to v squared over r, okay? And we know that force of gravity is equal to mass times gravity. It's really just the weight, okay? So now with all of these things that we just sort of talked about and found out here, some of them are just general equations, and some of them we just sort of had to deduce for ourselves. Let's plug that in and make our, just rewrite these two here. Okay, so sum of forces in the x, sum of forces in the y. Okay, sum of forces in the x. So we have n sine of theta is equal to m, and then we're going to plug in v squared over r. Okay, so we plugged in this n sub x, and we plugged in this v squared over r. Cool. All right, sum of forces in the y. We have n sub y, so we have n cosine of theta. And that is going to be, because we have 0 on the other side, I just added FG to the other side. Okay, so just rearranged that. So n cosine of theta is going to be equal to mg. Okay, so in this problem, we were given the value for the velocity. We're given that. And we're also given the radius, but we don't know the normal force or the mass of the object. So we're looking to cancel those things because we just don't know them. So, all right, I'm going to kind of do this a way that I think I'm going to be a little bit more intuitive. So let's say I don't know what n is. So I'm going to say mg divided by cosine of theta is equal to n. And I'm going to plug it into the first one. So, okay, so I solved this from this piece here. And I'm going to carry this first equation down, and I'm going to plug in n, okay? So I'm just going to take this n, put it in over here, and keep going. Okay, so mg over cosine of theta times sine of theta. And remember, my end goal is to solve for the angle, right? So I have the radius and I have the velocity, and this kind of allows me to cancel things a little bit more. So notice I have m on both sides, so I can cancel that. Nice. So now I have g sine of theta over cosine of theta. And remember that sine, right? Sine of theta over cosine of theta is equal to tangent of theta. So remember this trig identity. It will kind of help you combine things if you end up in a tough spot. Okay. Cool. Then we have, let's see, v squared over r on this side. So we're trying to solve for theta. So sine of theta over cosine of theta, we're going to say tangent of theta is equal to v squared over gr. Okay. So if we take inverse tangent of both sides, right, we can get theta is equal to inverse tangent of v squared over gr. Okay, so far so good. Cool. So if we plug in the numbers that we have, so we have velocity equals 13.4, I believe, meters per second, and the radius is equal to 35 meters, right? And gravity is equal to 9.81 meters per second squared. If we plug in all of those, we should get a theta value equal to 27.6 degrees. Okay. So Just to kind of recap what we did here. So we have a banked roadway to try to make sure the car doesn't slip. So what we did was we set up our sum of forces equations. We said that there's no acceleration in the y, and we wanted the normal force and the centripetal acceleration to basically be equal here. I know it's a little odd when they're facing in the same direction. It kind of seems like it should be accelerating in, even though it's not. So just really trust me on this one. But yeah, so we set these up to be balanced, and then we solved for our angle that would kind of keep everything in check here. Okay, and that's what we got. We got it is equal to 27.6 degrees.